Okay, hello y'all. If my Zoom people could just, I think I've shared the screen. If I could just see a show of hands to make sure everyone can see the screen and can hear me. Perfect, okay. You can put your hands down. Okay, let me get rid of that. Okay, so let's just take a moment before we get started to talk about where we've been and where we're going. So we have covered in about 2 weeks the basic features of Java. So you know about its memory management model with garbage collection, how it deals with pointers. You know that objects are not stack allocated, but only allocated off the heap. You've learned about the I/O system in Java. We've gone over some of the things with strings that are different. We've gone over enumerated types. So you know the basics of Java now. And where we're headed next is we're going to spend a day talking about Java's version of the C++ standard template library. And then we're going to move on into more exotic features of programming languages, and we won't restrict our attention to Java at that point. We will actually, when we talk about inheritance and module mechanisms, polymorphism, exception handling, we will be comparing and contrasting Java's mechanisms with C and C++. Now, C doesn't really support inheritance, but where there's comparisons, we'll be making them. So you will be expected in those homeworks to actually deal with 3 different languages, but the problems will be fairly simple. I won't be asking difficult problems. In contrast, on homework 2, you do have a somewhat difficult problem called PetDetective, and I'm actually going to spend the last third of the lecture today talking about how you solve it, because it's not simple, and but it's meant to give you some experience with graphs, with recursion, with search and backtracking. What else? With 2-dimensional matrices. So it's designed to give you some experience with stuff you covered in 140, 302, but which you may not be completely comfortable with yet. Okay, so first 50 minutes today, we're going to talk about the Java Collections library. Final 25 minutes, we'll talk about PetDetective. So basically the collections are a unordered, so we have collections, which is an actual interface in Java, which we'll get to in a moment, and we have something called map. So collections are unordered, and maps may be ordered or unordered. As you might imagine, maps are key value pairs, collections are just values. So under collections, there are essentially sets. You have a list type, you have a queue type, and you have a dequeue type. And then you have an ordered set and an ordered map. Now, in the collections, a map is not considered to be a sub-interface of collections. So that can create a little bit of an issue. They're part of the collection framework, but they are not themselves a collection. Okay, a collection is an unordered set or is a set of values. A map is key value pairs. Now you can convert a map to a collection, and I'll talk about how to do that, but it is not a collection. In fact, with maps, you can get collections in these ways. If you want the keys, you can use a key set method, and that will return a set of keys. If you want the values, you can say dot values, and that will return an iterable collection. So I really should not have so that will return an iterable collection of values. And you can say dot entry set. And that returns key value pairs. Specifically, it returns a set of map.entry KV, where this entry is a subclass or an inner class of map. And then you can get at the key and the value by saying entry dot get key and entry dot get value will get the respective key and value. So these three methods will convert a map to a collection that you can iterate over. You cannot directly iterate over a map. You can iterate over a collection. So an important facet of a collection is you can iterate over them. Okay, so everything in the collections library is imported from Java. It's not a capital, java.util. So both maps and collections come from java.util. And the collection is actually, so collections use interfaces which are abstract API or abstract types. So you're going to have to get used to this in Java, and we talk about it more with inheritance, but in Java, you are allowed to define a type that is devoid of implementation. You do it by prefacing it with the keyword interface. So for example, in the collections library, there's an interface set, and it then has a set of methods like get, put, etc. An interface looks a lot like a class declaration in a .h file in C++. But it has no class implementation associated with it. Okay, you can then define concrete classes which implement that interface. So for example, with the set class, there is a class called, I believe, hash set that implements set. And it guarantees when it implements, when it says implement, it guarantees that it implements all of the methods defined in the API of the interface. So these methods are the API, the application programmer interface. So when you see Q set on the previous thing, set, list, Q, and DQ are abstract types. There is no class called set, list, Q, or DQ. Instead, there are concrete classes that implement each of them. For set, there is hash set and tree set. For list, there are things like array list and linked list. For queue, there are things like priority queue, which implements a heap. For DQ, there are things like array DQ or linked list DQ that implement that. So each of them has concrete classes that implement them. Okay, so, and you can define, you can either declare a class, like you can say linked list, and then when you declare a class, you have to give it the type of the object that it's going to store. So let's say we wanted to store strings, you would say string, just like you do in C++ equals new linked list string. Or you can say a abstract type. I can say list string. So remember, that's an interface. But I can still say names. And now I can assign to it any concrete object, like say linked list, that implements that interface. And the reason I can do that is because I know that the linked list is guaranteed that it implements every method specified by the list interface. And therefore, I can declare names to be of this abstract type and then assign any concrete object to it that implements that interface. Now, it's important that you use these arrow braces because it turns out that originally you did not have this arrow notation. You just would say list names equals new list. And the idea was that a list would store objects. And you could downcast whatever you got out of the list to the appropriate type. Okay, and because you can always lose precision, you could put anything you wanted into the list without doing any typecasting. So you have to be very careful because it will let you do things like say list names equals new linked list. I'm sorry, it wasn't new list, it was new linked list down here. You can do this, and Java is happy with that declaration because you can assign to a list of names anything that stores a string, because lists can store objects. This can store strings. String is a subset of objects. But then if you start saying something like string x equals names dot say get 3, which gets the third name out of the list, you'll get an error message because names is a list of objects, not a list of strings. And you're saying, wait a minute, I assigned a linked list of strings there. Well, that's great. The compilers aren't all knowledgeable. You may have, at some other part of your code, reassigned names to point to something else, like a linked list of integers. So the compiler can't always determine that you've done that. Turns out that that is one of those undecidable questions. So when you try to write string x equals names.get, you'll get an error message. So it's important to always put the type. Now, under the covers, or under the hood, what's happening is when you say something like x equals, say, names dot get 3, that's what you write. What the compiler inserts is something that actually says x equals string names.get. So Java is still using the original implementation where it stores a list of objects. So in C++, when you define a, if you say, say list or linked list int, and then you say linked list string, in C++, you get two different versions of the code, two different versions of linked list get compiled. Not so in Java. In Java, there's one copy of a linked list. It stores objects. And the compiler inserts these downcasts in order to convert whatever you get out of a list to the appropriate type. And it does it for you automatically. But under the hood, Java is still using its original implementations of linked lists, array lists, etc., that only store objects. Now, what does that mean? It means that it can't store primitive types, because primitive types are not a class. So in Java, collections can only store objects, not primitive types. This is an important restriction. So Java collections can only store objects, not primitive types. So how does Java get around this problem? Because clearly you want to be able to store primitive types in collection objects. They get around it using a concept called boxing and unboxing. So what they do is they wrap primitive types in wrapper classes. And I showed you those wrapper classes on Tuesday. Every type has a primitive type has a comparable class with the same name, capital letter. So it's not all, I think actually int has integer. Most of the others are exactly the same name with a capital letter. And Java automatically, when you declare, so let's, actually I have a boxing example. So the easiest thing to do is show it to you. Okay, so here I have a map. I import a util.map. So that imports the abstract interface, then I'm importing a hash map. So then I create this boxing example, and see here I'm declaring a map that is a string with is the key, integer is the value. And you'll notice that when I do my put statements to put things into the map, I don't say, technically what I would have to say here is, make it an integer object. That's too much of a pain in the neck. They realize that. So they do that for you under the hood. The compiler does that. So that's called boxing. It's boxing a 3 into an integer object. Then when you get it out, so here I say int milk code equals product.get milk. And you'll notice that it boxed it into an integer object, but then it unboxes it back into a primitive type. So that's what's called box. When you hear boxing and unboxing, that's what is being referred to in Java, is that you can't store a primitive type into a collection object. So they're boxing those values into their corresponding wrapper classes, and then they are unwrapping or unboxing them when you assign them back to a primitive type. So if I run this, you see I'm just outputting what milk codes is. You'll see that it is happy to compile and run it. And when I run it, milk code equals 3. So it works seamlessly. So that is what is the notion of boxing and unboxing. Okay, so before we move on to the next topic, just a couple things. With a list, concrete implementations include array list and vector. Don't use vector. Okay, array list is what you should use. That is for single-threaded apps, which is what you're writing for the first part of the course. When we get to concurrency, then you will use a vector. But vectors are for multi-threaded apps. And because they're for multi-threaded apps, they're slower because they're doing certain locking and unlocking to avoid race conditions, which are unnecessary when you have a single-threaded app. So use array lists, not vectors for the time being. Okay, for the same reason, when there is a stack class that you should not use. Why is that? It's because it inherits from vector. Okay, so instead, the recommendation is that if you want to use a stack, you should actually declare an array DQ. Interestingly enough. So, and that's because an array DQ is optimized for single-threaded. So try not to, it's so easy to use a stack. It's better to use a array DQ. I'm not going to take points off if you use a stack. It's just less efficient because, again, it will be using locking, which is unneeded in a single-threaded application. Okay. Now, Java collection classes are a little clunkier to use because they don't use operator overloading. So the collection classes do not use operator overloading. So they're going to feel clunkier. So for example, in C++, you could have a map of, say, integer and string. I know this is an exact C++ code, but people. And you could write people 10 equals Brad. And this would insert Brad with the key 10. But that's overloaded, that array syntax. You can't do that in Java. So in Java, this is illegal. You can't do this in Java. Instead, you would have to say people.put, and you give it the key and the value. So here you would say put 10 in Brad. If you want to get something, you would say get and the key, like get 10. And a word of warning, the get command for a map returns null if the key does not exist. So if it is possible that null is a legitimate value, there's other methods. I think it's called contains. We'll check to see whether the map contains the key and return true or false, but get will always succeed. If the key does not exist, it will return null. So you run into the same problem with array lists. You can't say, so in C++, if you have a vector of ints, in C++, you're allowed to say something like x of 10 equals 5. You can't do that in Java. You have an array list, which is what you're supposed to use for an expandable array. So if you know exactly the size of an array, you can just allocate an array object. But if you need an expandable array, you use an array list. Okay, so it's integer. But now you have to say x.add to add to the end of the list. You say x.get 5 to get the index. And you would say set index value to set something. So again, you can't use array notation the way you could in C++. Okay, so that's one place where you can't do operator overloading. The other is in traversals. So in C++, you could write something like for a equals foo.iter, a not equal foo.end, a plus plus, and then you could say something like cout a. Okay, well, that's operator overloading, that's operator overloading, and you can't do either of those in Java. So in Java, if you want to get a iterator, you can still get the iterator, but then you have to use two methods called hasNext to determine if there is a next element, and next, which will simultaneously return the value at the current node. And advance. So next combines star with plus plus. Okay, so the scanner object is actually an iterable. You're actually using, when remember with a scanner, you can say .hasNext to see if there's a next token, and .next consumes the next token and advances. So actually scanner is implementing an iterator. Okay, so here's an example. Is this it? Yes. So here's an example of using an iterator in Java. So first of all, I'm importing a list, a linked list, and I have to import an iterator. So I create a list object and assign it a new linked list. Notice this is just a list, so that's an interface type. This is a concrete object. I add 4 names to the list. And then here's my iterator. So to get the iterator, I declare the iterator this is a abstract type. And every collection object has a iterator method that will return an iterator. So all the collection objects have an iterator method associated with them. Then I keep going while I have a next object, and you'll notice there's no increment here. Okay? The reason is when I use next to get the value of the current list node, it also advances. So it's advancing it. So this is an example of using an iterator in Java. So if I run this code, it should print Brad, then Nancy, then Harry, then Evie. Let's make sure it does. There it is, Brad, Nancy, Harry, Evie. Now, that is a little clunky. So what I suggest you do is use the for loop, the for each loop or enhanced for loop that the book talks about in, I think it's section 15.1. So I can say for string name my list. And then I can just say system.out.println name. Okay, remember in a for loop, you've already seen it with arrays, but you can use this with any collection object. Can't use it with a map, but you can use it if you use key set, values, or entry set. Then it will return a collection. So anytime you get a collection, you can iterate over it using this for loop. Remember, the value, the variable that holds each value, you have to declare it in the for loop. And then you give the name of the collection. So if we compile this, it should work. Of course, you have to compile the right one. Compiles. Still works. Okay, so again, I suggest you use the for loop. It's a lot simpler. Okay. So we've talked about general form. We talked about iterators, operator overloading. Primitive types, you cannot store a primitive type. You have to box it. Okay, last thing in the collections library is object ordering. So if you insert something into a map and it happens to be a sorted map, i.e. a tree map, it needs to be there needs to be a way to compare two objects. There is a generic sort method in the collections framework that allows you to sort a collection. Again, in order to do that, you need to have a way of comparing two objects. Now, in C++, you can overload the less than operator, the greater than operator, the equal operator. Again, Java does not have operator overloading, so you cannot do that. Instead, what Java does is it has two interfaces that you can use. One is called the comparable interface, and one is called the comparator interface. So when you want, so actually I'm going to show you an example. So when you want a class to be able to compare two objects of that class, you can implement the comparable interface. The comparable interface defines exactly one method called compareTo. Okay, remember strings, you can call the compareTo method. And you might say, wait a minute, doesn't object have a compareTo method? The answer is no, it has an equals method, but not a compareTo method. So if you want to make yourself be able to compare yourself with another object, you have to implement this comparable interface, and you notice you have to specify the type. And it has one method called compareTo, returns an int. It takes an argument of whatever type you said there. So you could actually make this be comparable to something else, but that's pretty worthless. So as you might expect, compare, what's expecting is if A is less than B, you should return a number less than 0. If A is equal B, you're supposed to return 0. And if A is greater than B, you return an integer greater than 0. So here, what I'm doing is I'm saying the natural order of comparing employees is by last name. And if the last names are equal, then I compare them on first name. So the first thing I do is say, if the last names are equal, then I return a comparison of the first names. If they're not equal, I return a comparison of the last names. So I'm saying the natural ordering of the employees is by name. So now I could insert an employee into a map, into an ordered map. It wouldn't matter for a hash map. A hash map would be happy not to have this comparison method because it generates a hash code. But a sorted map, a tree map, would require this. Which map did I? You'll notice, by the way, oops, yeah. Okay, so here I create an employee. What I'm going to do is simply insert a bunch of employees into a tree map. So notice I am creating a tree map here. And I am going to, and I'm sorting them by last name, obviously, because that's the way the comparison is done. Notice that the key and the value are both employee. The reason the key is employee is because I just made employees comparable using the comparable interface. Hence, I can use it as the key and the value. Okay. So I'm just creating a bunch of employees. So this employee makes $25,000, named Brad. last name Van der Zanden, put it. So I'm just creating a bunch of employees and I'm putting them into the map. And they're being put in there in sorted order. So the first thing I do is I go through and I ask for the employees by value or the value. So that gives me back a collection that I can iterate over, and I print them out. So I print out the last name, the first name, and the salary. Okay, so let's just do that part first. I'm going to comment out this next part. And as you can see, it's giving it to me in sorted order. So there's several Roushes there, and they're sorted by last name and then by first name. Van der Zanden sorted by last name, then first name. So the values will come back based on the sorted order of keys in a tree map. If in a hash map, it would be random, but I'm using a tree map here. Okay, next what I want to do is I want to print out the employees sorted by salary, not by last name. That's a problem because the comparison operator is based on last name, first name, not salary. There is a second interface that I can use to change this so-called natural order, and it is called the comparator interface. So the collections has a sort method. And that sort method will take a collection and optionally take a way to compare two elements. So if you don't provide it that way, they bet it will use the comparable interface. But this is saying, no, 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 don't use the comparable interface. I want to specify a different way of sorting. So I'm going to use this instead. Okay, so what is this beast? In C++, this would be a function pointer. So in C++, in the standard template library, there's also a sort method, and it takes a collection in the C++ template library, and it takes a function pointer. However, there are no function pointers in Java. So the way Java finesses this is you create an instance of a class. That class has the name of a known method that can be called. So in this case, you're going to create an instance of an anonymous class. So what you're doing is saying, okay, I'm create this new, says create an instance of a class that implements the comparator interface. The comparator interface has exactly one method, compare, not compare to. Takes two arguments, not one. Previously, so comparable, you are in the object. So one of the two arguments is yourself. The comparator is outside of the object and therefore needs two arguments. So in this case, I'm just using a cute trick that if these are numbers, I can just use subtraction to figure out which is greater. So if E1 salary is less than E2 salary, that subtraction will create a negative number. If it's greater than E2 salary, it will create a positive number. So this is a cute trick that you can use with integers or floating point numbers. So what this does is creates actually comparator is an interface. You can't create an instance of a comparator. What this is actually doing is creating an anonymous class that implements comparator. So you don't see it, but behind the scenes, what's going on is that Java is creating an anonymous class, in this case called map example, and it numbers them. Starting at 1, and it puts a $sign there. So we'll call it class map example $1 implements comparator employee, and then it will have that function body. It just copies this part into the main class definition. And when you compile it, and you look at the classes for map example, see the $1 here? That's that anonymous class that gets created. And it just numbers them. If you have multiple anonymous classes, it'll go up 2, 3, 4, 5, 6. Okay, and you see also the $employee class because that was an inner class. Class employee was an inner class, so it's also named with map example as its prefix. Okay, so by using that comparator object, I am able to create a new sort order based on salary. So
I have a question.
the first thing I did was I actually I took that employee map.values and I stuffed it into an array list. I'm wondering if I could sort that by itself. So I'm actually going to try something, okay? I'm wondering whether I needed that statement. So I'm going to try to sort it directly. So I want to see if I can just say employee map.values. I know why that does. That doesn't work because it creates a temporary list. And then down here, I have no way of getting to. Actually, though, let's do this. Instead of that, let's just say this is a collection of employee. I'll call that list. So what I'm trying to do is stop myself from having to create a totally new list because that's expensive. It's going to create literally a deep copy, which is going to slow everything down. So what I'm trying to see is if I can get away with list is just creating a pointer to it. It's doing a shallow copy. So I want to see if this works. Not find symbol. That's right, because I did not import it. No, I did. Import JavaCollections. I have to call this collections. Let's try it again. Let me check something now. So values returns a collection Okay, so I did, whoops, I had it, okay. So I have to, I think, import java.util.collection. So collections is the framework. Collections is a class. Collection is an interface. So I have to come down here. Still not happy. No suitable method found for sort collection. Huh, that looks very nasty. Okay, so the short answer right now appears to be that's why I did it, because I could not apparently figure out a way to do it this way. So it looks like the reason I did it this way was because it would sort a list, but it wouldn't sort a collection. I'll look into that, see if I can figure out why it won't sort a collection. But at any rate, what this is doing is it takes that collection, gives it as an argument to array list, it creates a completely new array list. And now I can sort it. So this should work. Yep. So first it sorted by last name, and now you can see it sorted by salary. So 10,000, 25,000, 50, 50,000. And you'll notice right here that. So this was the original order of the collection. And in that collection, Nils Rausch was before Smiley van der Zanden. And when we're done, it's the same. So Java uses a stable sorting algorithm. Now, is quicksort a stable sorting algorithm? It is not, correct. So Java does not use quicksort, it uses merge sort, because merge sort is a stable sorting algorithm. So just so you know, the sorting algorithm used in the collections framework is merge sort. It is not quicksort. The reason they use merge sort is because it is a stable sorting platform. Okay, I've gone through a lot, but rather than take questions, I know you may have them, but I have about 25 minutes and I really need to cover PetDetective because it is a rather complicated program to write. So, question 2 of your next homework assignment asks you to implement an algorithm that will solve this game that is offered by Lumosity. So the backstory is that so you need to turn pets to their home. Sorry, there seems to be no way to kill the noise. You have to listen to the noise. So you get 16 units of gas here. And what you need to do is take the car. So that used up a unit. And now I can deliver it. Now I'll get a fox. That used up another unit. Now if I deliver the fox to the fox home, that's 1, 2, 3 units of gas. So now it's down to 11. Now I have a turtle. So my next choice is I can go all the way to the turtle home, or I can pick up one of the 2 remaining animals. But I cannot go to the armadillo home because I have no armadillo in the car right now. So next I go to the armadillo, select it, back to the armadillo home. And I have 6 minutes of gas left, and you can see it's full. So I go to the dog. Okay, so the idea is I need to find a way to deliver those animals to the home in the specified number of guests. And there's a further restriction. I can only have 4 pets in the car at one time. So I can't have an unlimited number of pets. So as I collect pets, you see they end up in the car. But I can't put more than 4 of them in there at a time. So this actually isn't that hard to solve. I just obviously do it by blowing past the turtle home without delivering the turtle. But it gets a lot more complicated. When you get to the highest level. So when you get to the highest level, it's very hard to solve. And in fact, I discovered that Lumosity sometimes gives you an unsolvable puzzle. It's annoying. So I once got so frustrated, I figured there must be a way to write a program to solve it. And there is. And then I thought, wow, this is such a good program, illustrates so many principles of 140 and 302 that we're going to use it as a homework problem in 365. So this is actually an MPC problem. For those of you who took 302, the word Hamiltonian circuit may or may not ring a bell, but what this problem is actually a Hamiltonian circuit. We visit each animal or home once, and we have to do it within 37 steps. So it turns out it's a Hamiltonian circuit, it's MPC. A good way to solve it is with a recursive backtracking algorithm. So you saw that in 140 with whether I'm not sure if those two clips are short from the How about at home? Anyone there? Did Dr. Emmerich go over Sudoku in 140? Did any of you take 140 from Emmerich? Okay, that might be it. Okay, so at any rate, you're going to use an algorithm that's very similar to Sudoku. So I guess here is the kind of solution that you have to do. So step 1 is you're going to represent that grid as a graph. In fact, your input file is as a graph. The first element in the file is the number of gas units, but after that, every line is an edge with a from vertex. After that, every line is an edge with a from vertex, a to vertex, and it's actually undirected, and a distance. So the first thing you're going to do is you're going to read in this graph file and you're going to create a graph. Okay? Now, in order to solve this problem, the next thing you're going to have to do is find the distances, shortest distance between each pair of vertices. So vertices are pets, the car, and the pet home. Okay? So you need to know the shortest distance between each pair of vertices. Lumosity automatically chooses the shortest path. When you click on a pet home or a pet, it automatically chooses the shortest path for you. Okay? But you have to know in order to solve it, what is the shortest distance between each pair of vertices? And you don't know that. You only know the distance to your immediate neighbors initially. So you're going to use something called the Floyd-Warshall algorithm, which I'll get to in a moment. Before we get to that, let's assume that you have run that algorithm and you know the shortest distance between each pair of vertices. The third thing you're going to do is essentially, my recommendation is a depth-first search or depth-first traversal of a search tree. So what is the search tree? First of all, it is too big to keep in memory because it's exponential in size. But basically, the car is at the top of your search tree. It's the root. Then you choose a move. Your first move can be to any of the pets, like pet 1, pet 2, up to pet n. That's your first move. You can't go to a pet home on your first move because you have no pet in the car. So if you go to pet 1, you next have a choice of going to pet 1 home, or you can go next to pet 2 or to pet n. Okay, if you go to pet 1 home, you now have a choice of going to any of the remaining pets, P2 through Pn. If you go to pet 2, you now have the choice of going to pet 1 home, or pet 2 home, or to any of the remaining pets. So this is an enormous tree where essentially every possibility is enumerated. But you can't represent that tree in memory, it's too big. So all you're going to be doing at any one time is keeping a stack of where you are in that tree. So for example, if I've gone here, yellow's not a good one. We got, that's not too good either. Let's go for black. Regular pen. So let's say we've gone here, then to here, then down to pet 1 home. All you would keep is information about this one part of the search space. This is going to be very much like the Sudoku puzzle that you saw back in CS140, okay? Where you have a number of options, you select the next option and go to it. You update things. So for example, if I go to pet 1 and then I go to pet 2, I need to indicate that there's 2. How do I get rid of? Unfortunately, there we go. Okay, so if I go to pet 1 and then I go to pet 2, I need to keep track of the fact that there's 2 pets in my car and that I have a capacity of 2 left. Because if I get to having 4 pets in the car, now my search is dwindled down to exactly 4 vertices. I can only go to one of the 4 homes. I can't pick up another pet. So one thing I have to keep track of at all time is the number of pets in my car. So if I go and pick up a pet, I add 1 to the number of pets in the car. If I go to a pet home, what do? Decrement the count. Okay? So if I fail, remember with Sudoku, if you failed, you had to back out the number that you had put down. Same thing here, if you fail and you picked a pet, then, so if I was at 1 and I picked a pet, so I incremented the number of pets in the car to 2, I'm going to have to revert back to 1 pet in the car. Same thing, if I had 2 pets in the car and I went to a pet home, thus decreasing the number of pets in the car to 1. If it fails going to that pet home, I have to restore the pet back to the car, meaning I still have a count of 2. So this is, the search strategy is very similar to the Sudoku puzzle that you did with Dr. Greger or Dr. Plank. So go back and refresh your memories about how that is done. Okay. And to make this fast, you should go to the nearest pet or the nearest vertex first. It won't always work, but I guarantee you, your chances of succeeding are much better than if, for example, you go to the farthest vertex from you, because that's going to quickly deplete all of the gas units in your car. So my recommendation is that for each vertex, keep a, so once you've done step 2, which is find the shortest distance between each pair of vertices, then step 2A is for each vertex, keep an adjacency list of vertices, sort it in ascending order of distance so that you always start with the closest vertices, because they're the ones that are most likely to succeed for you. So I suggest that after you finish with the Floyd-Warshall algorithm, that you'll basically have a vertex, a matrix. It'll be square, and you'll have like pet 1, pet 2, pet 1 home, pet 2 home, and you'll have distances, pet 1, pet 2, pet 1 home, pet 2 home. You'll have distances, okay, on the diagonal it's 0. It'll be like 3, 2, 8. What I suggest you do is sort each row into ascending order. You could do a linear search each time to find the next smallest element, but it's going to get very fast. You're going to get confused because which ones have you already gone to and which ones haven't you? Just a lot easier if after you finish the computation of the distances for each row, you simply sort the vertices into ascending order of distance, which means you can use the collections.sort method. Okay, so I suggest you use that. Okay, so how do we get step 2 is the Floyd-Warshall algorithm, and you may not have seen that in 302. So go to homework. It's actually pretty simple, the idea. So the idea behind the Floyd-Warshall algorithm is you number the vertices from 0 up to n. Actually, n minus 1. Then what you do is you assume it's an inductive thing. So you find the short, let's say that you have the shortest path from vertex I to vertex J. Don't draw. Right. So you have this meandering path, and it goes through all vertexes less than k. So what you do at step k is you see, is there a path that goes from vi to k and then from vk to j that is shorter than the current path that goes from vi to vj. So for example, if this path is 10 and there is a path from vi to vk that is 3 and a path from vk to vj that is 4, then at step k, you say the new shortest path from vi to vj is length 7. So it's a very simple algorithm. You simply go through the vertices from 0 to n minus 1 or 1 to n, and you just look at two pieces of information, the current shortest path and the possibility of going from vertex I to k plus from k to j. Your starting matrix is the distances I gave you when you read in the graph. So it is, you initially have some vertices that are directly connected to each other, so they'll have a value. The rest of them are infinity. Okay, and you'll fill in those infinities. So the algorithm, you can basically do it almost line for line from this one. Is initially you have that matrix I just showed you where you filled it in for the vertices that are adjacent to each other, directly connected. Then you assign to the remaining vertices some arbitrary infinity value. Okay. And then 4k from 1 up to the number of vertices, and then for each pair of vertices, so that's the I and j, so for each pair, all you're doing is checking to see whether the current distance is greater than the distance from I to k plus the distance from k to j. And if it is, then you assign this new distance here. So it's actually a very simple algorithm.
Dr. Vandersanden?
Just a sec, one thing, yeah, and then I'll get it. The one gotcha here is if you actually initialize to infinity, which in Java does have an integer dot maxint. If you initialize everything to integer dot maxint, you'll get arithmetic overflow. Because if you add two integer dot maxints together right here, that will give you arithmetic overflow. I learned this the hard way. So I will guarantee that there is no distance greater than 1,000 for this assignment. So you may assume for this assignment that 1,000 represents infinity. Okay, so no two vertices will be separated by more than 1,000 units. Okay. The other thing I will tell you is sometimes the searching can take a couple minutes. So this is one time when super fast computers run up against NP completeness. Okay, questions?
I had a question about that first for loop.
Go ahead.
In the war algorithm for the first loop. So when I wrote this portion, I actually did not include that because from my interpretation, the first for loop is
This
putting
one
in
right
the
here, right?
original distances between
Yes.
the distances between
This one you don't need. So the question, okay, this loop you do not need because you've already filled it in.
Yes.
This loop is already done. You've already filled it in when you read the graph.
Yes.
Okay. This one you may or may not have done. That's setting the diagonal to 0.
The rest of it I actually did implement, but it was just the first
Yeah, the first loop you do not need because the first loop, you're right.
Okay.
The first loop is unnecessary because you already have it. That's from the file that you read in. Other questions? Okay. So I shall let you all go in that case. I will see you on Tuesday where we will start talking about inheritance. And good luck with
I
the
have,
puzzle. I will be looking at email periodically over the weekend. So if you're having, if you're struggling, I'm sorry, Piazza over the weekend. So if you're struggling with it, you can ask questions on Piazza.
I have a quick question.
Mhm.